Use normal approximation to calculate the probability that a binomial random variable representing an experiment that is done 25 times with a 20% chance of the outcome we wish to count is greater than 1. So we get more than one of the outcomes we're interested in. What's the probability that happens? Okay. So it's a binomial random variable, but if we're going to use normal approximation, we should figure out the mean and the standard deviation. So 25.2, and we'll just make a note, it's greater than 1. That way I don't have to keep going back and forth between the various pages. So we need the mean of our binomial random variable. So the expected value is going to be 25, the number of trials, times the probability of the thing we're interested in happening. Now that's, 0.2 is really just a fifth. So the mean here is 5. Standard deviation, square root of n times p times 1 minus p. So the 25 times 0.2, we just saw is 5. 1 minus 0.2 is 0.8, which is really 4 fifths. So we get square root of 4. So the standard deviation here is 2. So let's introduce a good approximation. So let's let y be normal with the same mean and same standard deviation. Okay, so that's what we need. That gets us started. Now, what we want to do is change the probability here in terms of this binomial random variable, which is a discrete thing. It only counts 0, 1, 2, 3, and so on. We want to trade that for a probability in terms of our continuous random variable, y. Okay, now because we're using normal approximation, we might even bother to mention y is a good approximation. Okay. So what does that mean? Well, if you've got a good approximation, you can trade probabilities. And the way you can do that, and the way you can easily see how to do that, is using a sort of mock histogram. So our binomial random variable counts 0, 1, 2, 3, 4, the number of successes. The average is around 5, but it's going to actually keep going up to 25. We're not really interested in all of those. We just care what happens around 1. And I have really messed up the spacing here. I try and make sure my histograms look a little decent. So we'll draw a slightly better version here. But as I'm always fond of pointing out, it's your picture. As long as you understand what you mean, you're fine. We don't really mark histograms in math courses anymore. Okay? Now, what do we want? We want the probability that we have more than 1. So which of these boxes are going to be shaded? Well, 2 is something that we could have. We could have 3 successes, 4. We could keep going, 5, 6, everything over here. Really. But not 0 or 1. So where does our shaded area, where does our shaded region start? Well, it starts halfway between 1 and 2 at 1.5. So this is what we're going to trade. This is what we're going to use to trade our probabilities. Okay. We want this probability greater than 1 for our discrete random variable. With y being a good approximation, we can trade for the probability that y is greater than 1.5. Y is a normal, sort of a bell curve. And so the area under y that starts at 1.5 is meant to be the same as the red area, those shaded boxes, the ones whose values are greater than 1. So we switch from a discrete random variable to a continuous random variable, a normal random variable, using histograms, good approximations to sort everything out. And so now, this is just a question involving a non-standard normal. What we can do is we can trade this for a probability involving our standard normal z. What do? Well, you take the 1.5, you subtract off the mean, 5, that we worked out, and divide by the standard deviation, which was 2. This gives us a z-score to compare. So z needs to be bigger. Notice the sign here doesn't change. 1.5 minus 5 is going to be negative 3.5. If you divide that by 2, 35 divided by 2 is going to be 1.7, well, 17.5, but we'll shift the decimal over. So we need z to be bigger than negative 1.75. That's not something I can easily look up in our cumulative distribution table for the z-scores. Okay, negative 1.75, that's a negative z-score. We see z here is bigger. It's a bigger value. So we want this area shaded off to the right here. Okay, so what can we do? Well, we can flip the area. Okay, flip the whole thing over, use the symmetry of the standard normal curve, and now the negative z-score flips around and becomes positive. The area that was shaded to the right now becomes an area shaded to the left. So the probability we want is the same as the probability of z being less than 1.75, and that can be looked up in the chart. Okay, cumulative distribution table, 1.7, hundredth digit is 0, 1, 2, 3, 4, 5. So our answer should be 0.9599. Okay, so 96% chance that we'll get more than one of whatever this binomial random variable is counting. So there's our final answer. Although if I was trying to make myself very clear, I would probably summarize using the original discrete random variable that we were talking about. And there we go. So there's my final answer expressed in all its glory. So we had a discrete random variable, which will often be given. We shift it to get a probability in terms of a continuous random variable that is normal. And then we treat the problem as we have before. Shift to a standard normal, look up z-scores in the table.